All right, so today I'm doing a talk on Wi-Fi denial of service. This is probably my last talk at IASG while still here at Iowa State, so hope it's good. This is actually based on a project I did a year ago as part of Computer E 537, which is the wireless security course, where you talk about a bunch of different stuff from Wi-Fi security, which we're talking about today, to radios, jamming, a lot of cool stuff like that. So recommend that class if you want to learn more about that stuff. And so this is the final project I did most of the semester and wrote a paper on and actually made a tool for. So we'll see all of that shortly, as well as the tool and what it can do. So disclaimer, as usual, I'm not responsible for what you do with this information or what I've provided, the tool I provided. Things might be illegal if you're attacking networks that you don't own or don't control or don't have permission to test. Also, some of the attacks may affect other networks in collateral damage fashion. If you try to launch an attack on your own network, it might affect someone else's network or someone else's computer, so be aware of that. And it may be illegal to use this stuff in the wrong way. So just be careful, I'm not responsible for your choices. So rules of this talk, as usual, ask me questions, and there are no rules except for what the previous slide said. So, all right, so we're going to start out with a review of 802.11, what that means. Talk about some security issues with Wi-Fi, talk about an attempt to fix 802.11 with the protocol called 802.11w, talk about some vulnerabilities that exist in that as well and exploit them if applicable. And lastly, a bonus topic that I've decided to put together today that might be interesting. So, review of 802.11. Some of this is boring stuff, but 802.11 is basically what we know as the Wi-Fi protocol. 802.11i was ratified in 2004, and that's what we know as WPA 2. And it uses AES to encrypt using either a pre-shared key, so that's how you enter your Wi-Fi password when you're connected to a network, or you can use EAP exchange, 802.1x, so that's what EduRoam uses here at Iowa State. Instead of typing in a single password that everyone shares, you type in your credentials for Iowa State's domain. Nice shirt, Logan. And so with that, you never actually send the password over the network, at least for the pre-shared key. So, and that means you can't intercept that handshake. You have to, each side proves their own knowledge of the key using some magic crypto that we're not going to talk about. But basically, if you were to sniff that handshake, you would not get the password. You'd get some things that can help you find the password, but the password's not there. So we'll kind of see a little bit of that, but that's not the main point of today. So management frames are pretty important in Wi-Fi. So management frames are what control everything from authentication to de-authentication, association, disassociation, etc. They're beacon frames. So beacon frames are how Wi-Fi access points announce their presence, so what SSID they have. If we pull up in Wireshark here, and I just look at traffic that's been going over the air, it's currently filtering out. It could take a couple seconds here. All right, so all this garbage is just from the Wi-Fi signal in the air right now. So you can see like a beacon frame right here. There's a beacon frame, I don't know if you can see, but it's advertising the SSID ISU cardinal. So that's what a beacon frame is. It's just saying, hi, I'm an access point. You can connect to me. Here are my capabilities. So there's lots of those. I think most access points send them out every 1/10 of a second. It's configurable, but it's pretty frequent. And probe request responses. Probes are what client devices do, like your laptop, if it's looking for a hidden Wi-Fi access point. The responses come back from the access point saying, you found me, I'm here. There's also control frames, which are less frequently used, although I did see a lot of them. All these request to send and clear to send, those are control frames, and what those do is they're used when there's lots of devices or there's like a wide range of coverage sort of for a network. So one device that's trying to transmit might not be able to hear another device transmitting at the same time, and you can't have them at the same time because there'll be a conflict in the middle. And so what this does is before someone can transmit, they request to send, and then the access point will say, you're clear to send for this much time. And then the client will send for that much time and then hand it off to the next person whose turn it is. And often that only applies to frames over a certain size, so it doesn't always apply. But apparently some of the networks here are using that. A lot of networks don't use that by default, but it's a setting you can turn on often in the advanced options. And so we'll see how a lot of this stuff can be used to kind of exploit these networks and break how they work. So kind of a review here of how devices authenticate with the network. So keep in mind, this is all before your WPA2 authentication. None of this involves even that. So the terminology is kind of confusing. So when they say authentication here, it doesn't actually mean you've authenticated with the PSK or whatever. It's just a very early stage in authenticating with the network. So the first thing a client does, it's in the de-authenticated state, state 1. It'll send an authentication request. Sorry, I gotta log into the second laptop here. So you first send an authentication request to the access point. In pretty much all cases, it'll just say right away you're authenticated. There's no actual authentication. It's just kind of the way the protocol started out, and they never really changed it. Once you're authenticated, you're in state 2, and then you want to be associated as well. So you try to get to state 3 by asking the access point for an association request. It replies usually saying you're associated. Now you're in state 3, and in state 3 you can finally do whatever else you need to do. So if it's like doing the key exchange to actually authenticate with the network, or doing EAP to use your Iowa State credentials, for example, on ED or Rome. So that's just kind of the basic state machine for an access point, how devices are authenticated with it. And so the security issues. So we talked about management frames, how management frames are what allow devices to be authenticated or de-authenticated. They also control the association process, and they are, that's where the beacon and probe frames are as well. And so none of those are authenticated. They're all for one, plain text, as we saw in Wireshark. I can just see all of these different management frames. That's what all these are. Most of them are, at least. We can filter by, got a lot of packets here to filter through apparently, but. So they're all gonna be just in plain text. And not only can we see them, we can also craft them and send them to the network to do whatever we want. So, oops, did the wrong number. So that's kind of significant for de-authentication. So pretty much anyone can say, hey, that device, stop talking to the network. You could spam the entire network with de-authentication requests and make everyone disconnect from the network. And that's pretty easy to do with a lot of tools are out there for that, like AirReplay NG. This is actually my custom tool we'll see a little bit later, but doing a basic de-auth attack. In these videos, the top left will be the device constantly pinging a IP address on the network. The bottom window is going to be, the bottom left window is going to be the client's debug output for its WPA Supplicant. And on the right, we're gonna see my attack tools in action. So I'm running a command up there. It's going to say deauth once it starts. And you notice the ping stopped happening over there, and a bunch of output starts coming out on the bottom left. So that's the client trying to reconnect. And the pings are going to stop as long as we are running that script. And after a few seconds, it'll finally be able to reconnect with the network, and the pings should resume. Maybe not. Maybe the video ends before that. I don't remember. But yep. So now it resumes pinging because we stopped the auth attack. So anyone can do that. I was not authenticated to the network when I did that. And that affects all networks, whether they require authentication or not. So open networks or secured networks, you can do that. The second point here is anyone can send those control frames without authentication. So we talked about how the clear to send, request to send, you can request some time basically on the air to send your data. Let's say you craft one of those that has a really long, you request a really long amount of time, and you keep sending those. You could request all of the airspace in theory, and no one else would be able to request time because you've used it all up. And so I guess what's the consequence of these de-authentication attacks? Well, obviously, for one, anyone can kick devices off the network. You don't want that. It makes it not very usable and not very friendly for people using it. It also, sometimes some of these attacks can be like one packet will hit the access point and the whole thing kind of loses state and breaks sessions, so it will not work from there on with just one packet. Also, if we're trying to grab someone's password for their network, we can't just steal it off the air, but we can grab some pieces that help us find it. And de-authenticating them causes them to reconnect and then do that key exchange again, which gives us a better chance to crack it. It's also important because, well, these MAC layer attacks, they're using the 802.11 protocol. They're not at the physical layer. They're not just jamming radio attacks. They're harder to trace often. It's not like if you have a jammer, you have to put a jammer somewhere in range of the access point and then kind of leave it there and have it keep jamming the whole time. which is kind of tedious, and it's easy to find a jammer. But with MAC layer attacks, sometimes we can just send a couple packets here and there, and it will do its job and kick devices off the network just as effectively. And so this is bad because we could take down networks at companies, so work doesn't get done. Universities, so you can't study. If the Wi-Fi was down right now, I couldn't even have the slideshow because it's on Google Drive, so that wouldn't be fun. Imagine if you have a Wi-Fi security system, your cameras are connected over Wi-Fi, and I just come over and I de-authenticate them. Well, now you're no longer recording someone breaking into your building or whatever. And also, critical infrastructure is often connected to Wi-Fi, even though it probably shouldn't be, and you could easily break it by disconnecting it from there. So we'll see actually in practice how some of these attacks work. But so as I mentioned earlier, we have 802.11w, which is a kind of a proposed solution to some of these problems. So it has something called protected management frames, or PMF. And so a lot of those frames we talked about, like the de-authentication, disassociation, that will just drop a client off the network, they're now protected using this system. So you can't just de-authenticate somebody. You first have to be authenticated with the network. So the problem with that is still, if you're able to get on the network, you can write these frames and kick people off. But if it's a network you don't have access to, you cannot do that. So as a stranger who comes up to your network and they don't know the password, they cannot de-authenticate you using those de-authentication packets. Now, there are other ways, which we'll see shortly. But that's the main one we care about. The other three things are, we don't really care about those too much. I think I talked about those in my older talk. But the main one is the de-authentication. So you cannot use those packets anymore using 802.11w. But there are still some problems with this. We saw that it does cover de-authentication and disassociation, but it does not cover authentication, association, beacons, probes, and control frames. So all those other things, all those other management frames and control frames are still unprotected, and you can still craft them on a network that does use this protection. There's also additional complexity added to this system that causes potential for deadlocks. So as I mentioned, sometimes you're able to craft one packet to the access point or the client, and it creates like kind of it creates a deadlock where the devices are out of state and cannot correct their state on their own. So still, even with this in place, anyone can spoof these frames and take down your network. So in the wild, this is actually not used very often. It sounds like it should be used because those frames seem like they should be protected. But most devices will not use it by default. A lot of Cisco hardware seems to have the option, at least. I have not seen it on any consumer devices, or at least routers. Most client devices, like your phone or laptop, should support it, and they'll use it if it's available. But again, it's not available very often. Most operating systems support it as well. And some custom firmware for your router might have it as well, but I've not really seen that much of it. You usually have to, if you want to set it up on an access point, you have to do it pretty much manually or buy some expensive Cisco product to do it. So I guess the project goals of this presentation were to figure out the security of 802.11 and 802.11w on modern software. And I read a paper on various attacks against 802.11 for denial of service, and I went out to see if they were actually if I could actually implement them and perform these attacks in real life. So I developed a tool as a result to attack these systems. And we'll see a few of these attacks in practice against real access points that I set up in a test environment. So I did this environment by having one system each for an access point, a client, an attacker, and a monitoring system, so I could capture the packets and see what was happening. I used host APD as the access point, and that's just it's an application or a program for Linux systems that will create an access point. You can install it on your laptop or whatever to create an access point. And Wpa Supplicant is the supplicant, which is basically the client machine, or the client program that authenticates with a WPA network. And Wpa Supplicant is very common. It's what's used on Linux systems, on Android phones, on many devices like that. So it's a pretty realistic setup. A lot of devices probably don't use host APD, but some will as well if they run Linux. So the first attack is kind of a deadlock type condition where we have, in this graph over here, or this chart over here, you can see we've got a client who's already connected to a network. They're already authenticated and everything. An adversary will come and send a single authentication packet to the access point. And that's that authentication packet we talked about earlier. It doesn't actually fully authenticate you, but it gets you into that state 2 of the state machine. And so once that happens, the access point thinks that the client lost their connection somehow and is trying to reconnect, even though the client actually is still connected. So the access point starts to try to re-authenticate with the client, and the client gets kind of confused because it doesn't know why it's re-authenticating. So it ends up deleting its keys. But at that point, the access point thinks it's trying to authenticate, and it gets confused as well. So it kind of keeps cycling over and over again out of state. And so in theory, sending just one packet to the access point would make the client not be able to reconnect for a while. So I have a demo of this attack in my tool. Same as before, top right is the attack, left is the pings, and the bottom left is going to be, I think that's host APD. So it's sending ZZZ to put the client to sleep, basically. You can see the pings stopped happening. And then shortly it'll be able to restart again. So what happened here is the client got kind of confused because somebody else tried to authenticate with its MAC address, and the access point started talking back to the client and basically kicked it off. And so what I found with this is that even though in theory it was supposed to be viable against 802.11w, it was not, but it was very effective against 802.11w. So you could use that instead of a regular deauthentication attack to kick devices off your network. And so what happened was the access point deleted the keys and kicked the client off without telling the client. So the client was kind of sitting there like, why can't I talk anymore? So that sort of worked well in an unexpected way, but it did not beat 802.11w there. The second one has to do with ePaul, and a lot of this stuff is a little complicated over here, and it's not too important. But basically what happens is when we're doing that key exchange between the client and the access point, when you're actually proving you have knowledge of the key, it's a four-way handshake. And what you can do is right after the access point tells the client that it's ready to go, or I guess it's the other way around. After the access point tells the client that stage 3 is complete, we can send an unprotected deauthentication to the access point, and it'll think the client did that, thus kicking off the client, even though the client's still trying to do stuff on the left here. So we kind of just snipe it here. It's kind of a race condition. So there's message 1, message 2, message 3, and then we snipe it with the deauthentication, and then message 4 comes. And the reason this works is because even though we said in 802.11w those management frames are encrypted, they're not encrypted until we've successfully finished with this key exchange here. So we can do that attack to see if we can actually carry it out. I'm not sure what the results of this one were. It might not have worked too well. So on the right, we're sniffing the traffic, waiting for that third message. But I think I had some trouble actually getting it to happen in time. So it did find the packet, and it did try to deauth it, but as you can see, nothing really happened to the pings, and we stopped it down there. But I think I tried it again, just spamming that deauthentication the entire time the client's trying to connect. And let's see if it works here. Nope. So now we're just spamming deauthentications without waiting for that race condition, and it still doesn't kick off the client. So some of these attacks actually didn't work out in the end, so I found that out. But probably the coolest one is the next one here. So as I said, yeah, the race condition was hard to achieve since that it happens pretty quickly. We have to snipe it at the right time. But in general, the deauthentications did seem to be fairly effective during a handshake if you could pull it off right. And what even made it harder to do this attack was that the client implements the deadlock recovery protocol. So even if it gets lost and confused what it's trying to do, it should be able to recover from it. So that's no fun. But this next attack is the CTS nav, which is the one I talked about with those control frames instead of management frames. So it's a feature when you're in a congested space to make sure devices kind of wait their turn before they send. And so we can spam a bunch of clear to send frames to a non-existent address. That's how it works. So we say this person at address ABC is allowed to transmit for the next second or something, and that address won't actually exist. So while that non-existent device has time, no one else can transmit, and everyone else has to wait until it's done. And I actually didn't have any luck with this one because I couldn't get the CTS RTS working on my test network, but it might work on a network that actually has it properly set up, like here, but don't try it. So this one is probably the most fun that I kind of enjoyed finding this one. So there's this feature on 5 gigahertz networks that is, it's for radar detection. So if you have like a 5 gigahertz network near a military base, there's kind of a rule in place that says if they start transmitting on a certain frequency in the 5 gigahertz band, your access point has to switch channels to avoid interference, which kind of sounds weird. Didn't really know that was a thing, but apparently the 5 gigahertz band on your consumer router could interfere with some military communications. So they implement this protocol to basically switch the channel temporarily while someone else is transmitting. It's called DFS, which is dynamic frequency switching. And it's only for 5 gigahertz, but what's interesting I found is that most clients also do it for 2.4 gigahertz. So basically what we can do is send out beacon frames, so beacon frames advertising our access point, and we say in our beacon frame, hey network, we're now switching to this channel, although the network's actually not switching, but we're telling everyone it is. So all the clients switch their channel over to some other channel that the network doesn't exist on, and they're disconnected, and they have no idea what happened because there's nothing on that channel at all to tell them to go back or anything. So it's kind of a funny thing that happened as kind of a mistake on maybe on the implementation part, since it's only supposed to be for 5 gigahertz. And we can do this just by sending out a beacon frame with the same SSID or same BSSID as the network. So here's the video of that attack. So you can see on the bottom right here, we have the current channel that my client adapter is on. So it's currently on channel 1, which is where my test network's at. As usual, the pings are up there. I think that's the access point on the bottom left, but on the top right, we're running this attack, and we're gonna try to change it to channel 9. So what happens is we see some garbage coming on the left. That's the client trying to reconnect to the other network, I believe. And you can see in here, you see some channel 9s in there. So the client's actually hopping back and forth between channel 1 and 9 because it's following this protocol where it's supposed to switch channels on demand. And so this entire time, you notice the pings will stop. And I think I got it to where you could send only a couple of these packets and it would kick the client off for a while as it tried to figure out what channel it was supposed to be on. So it was kind of interesting to see this protocol abused in a weird way. So that one's kind of a fun one. And the point of all this is that none of these are prevented by the new 802.11w, which is supposed to prevent random attackers from controlling your network by spoofing management frames, because these frames still aren't protected like beacon frames. So it was very effective, as you saw in the video there. So remediation for a lot of that is to actually encrypt the control frames, which are the CTS, RTS ones that we didn't see a video for, but that attack where you can steal airtime could be prevented by encrypting control frames. The problem with that is every access point will share the same, they don't actually distinguish by access point. So everyone who's talking in the same area will respect those frames regardless of what network they're on. So it's kind of hard. How would you coordinate that? I don't know. Deadlock detection, as these more advanced features are enabled, there should be ways for both ends to recover if they get confused by an attacker's spoofing packets and throwing them in there. And lastly, protecting the authentication frame. So during that 4-way handshake, as I mentioned, that's all in the clear. What we could do to protect from having things interjected in there and attacks on the 4-way handshake is we could actually create an encrypted tunnel first, and then do the 4-way handshake inside that encrypted tunnel. So that would actually fix a lot of these problems with denial of service and stealing the 4-way handshake to crack the password. So that'd be beneficial in many ways, but I think we're still pretty far out from actually doing that. So I made a project for this, as I mentioned. It's on GitHub, it's open source, and I might update it in the future, maybe not, we'll see. It's kind of dead at this point, but on the right here, I've got a video of it in action. It's got an interactive mode as well. So you fire it up with your interface name, and it shows you a bunch of networks in the area. The ones that are in purple are using 802.11w, so they use the protected management frames. You can see all those networks. I have my one at the top, which is protected by 802.11w. It lets you pick an access point from the list. We picked number 0, which is my test one. Then it will try to discover clients on the network. We got one client that we're going to target. And then again, it lists out the attacks you can run. I didn't actually implement all of them. I think I did most of them except maybe 4 and 5. The other attacks do at least attempt to work. I don't know if they actually do, but we saw that number 1, 2, and 7 should definitely work. So it's the same attack we just saw with the channel hopping, but just from the interactive tool that I have here. So same as before, it's successful in kicking off the client. So yeah, check that out if you're interested in seeing how it worked. It was mostly done with Python and Wpa, which is a packet creation and packet analysis library basically for Python. You can just create packets with it, and it's kind of an easier way than just using the raw, the sockets library. You can put together each layer of a packet together with like IP objects, TCP objects. It kind of does it for you in a nice way. But that was kind of fun to learn how to use Wpa to craft wireless packets, and you could probably do a lot more attacks with it as well. So that's the end of the main talk, but I did prepare a bonus topic as well here. So references, stuff like that. Any questions on the stuff I talked about with denial of service attacks on wireless access points?
How much of that's going to be protected with Wpa 3?
That's a good question. I've not looked into that too much. I probably should have before doing this, but I don't think they protect the management frames. I could be wrong. I've looked into it a little bit, but that would be nice if they actually did that. I think most of the focus on that protocol, they don't even fix like being able to capture the four-way handshake, if I'm not mistaken. I could be wrong about that, but I've read a little bit into it, so I don't know if I can fully answer that. But that's interesting, yeah.